I'll be talking about the joint work with Elette, Itai, Niv, Yuval, and Nathan. Alice and Bob go to New York and they want to meet up. We all know that it might be a challenging task to find each other without a GPS. One solution to the problem is that if Alice and Bob scan the entire skyline and search for the Statue of Liberty, then they can transmit their location relative to the statue, and then they can compute the relative location between one another. The problems with this solution is that a notable object such as the Statue of Liberty is not always present in our map. And moreover, if we do have such an object, finding it takes a linear time. So we search for a general and efficient method to communicate relative locations. For this, we introduce the concept of locality-preserving hashing for shifts, or LPHS in short. We say that the function h from n bits to the integers is a d delta LPHS if h can be computed by reading d bits from the input, and if the probability of a random strings x that h of x does not equal to 1 plus h of x shifted by 1 is smaller than delta. So in the example below, if the h of Alice's input equals to 9, then we want it with high probability that h of Bob's input to be 8, because Bob's input is Alice's input shifted by 1. We may think as the h of a string as the location of the distinguished object inside this string, because as we shift our string, the value of h should shift with it, except for a small probability. So the whole point is to have a good trade-off between d and delta. We want both d, the number of queries, to be small, and we also want delta to be small. As we will see later, we cannot hope that delta to be 0 unless d is large. So we seek for a good dependence between d and delta. There are a few details or variants to our LPHS definition. First, we consider the average case LPHS definition. That is, we wanted that for a random input string x, that the probability that the shifting property to not all to be small. However, we could insist that for every input string x, that the probability that the shifting property to not hold on our random LPHS to be small. However, in the paper, we show that these two definitions, except for highly periodic inputs, is the same. So in this talk, we will use the average case definition for convenience. Also, we did not exactly specify how our shifts are looking. We may use cyclic shifts of our input, and we may also use acyclic shifts. That is, in acyclic shifts, we chop one bit from one side of the input and insert a brand new random bit in the other side of the input. Again, in the paper, we show that these two definitions are usually the same, but there are a few differences, and in this talk, I'm going to assume the acyclic shifts. Moreover, for two-dimensional applications of LPHS, we need a two-dimensional LPHS. That is, we need a function h that receives a two-dimensional input and returns a vector of two integers. We again want that this h will return a distinguished location inside our input, and so we want that usually h of x and h of x shifted up by 1 to differ by the vector 0, 1, and we want that usually the difference between h of x and h of x shifted right, we want the difference to usually be 0, 1. So this is the definition of a two-dimensional LPHS. And we show the different constructions for both kinds of LPHS definitions. Later in the talk, we'll show a good construction for an LPHS. For now, I want to present several applications of such a good construction. The first application is algorithmic. We construct a nearest neighbor data structure for the shift metric. In this problem, we are given several input strings in advance. And in query time, we are given a new string, and we need to find the closest string in our database that is closest with respect to the shift metric. Other applications are cryptographic and include location-sensitive encryption. That is, we can encrypt a message so that only people who are physically close to us will be able to decrypt. And we also show an application to homomorphic secret sharing where this technique gives state-of-the-art solution in terms of communication of several problems. And we show how a good k-dimensional LPHS can give even less communication in such problems. The goal in our first application is to construct a data structure as follows. We are given m input strings, which we should pre-process and insert into a data structure. Then when we are given a query string q, then we should find one of the strings that we were given earlier that minimizes the shift distance between q and this string we output. So how do we use the concept of LPHS to construct such a data structure? For this, we define the notion of locality-sensitive hashing for shift distance. This object is a family of hash functions which satisfies that for every input strings x and y, the probability that we have a collision between the hashes of x and y with respect to a random hash function from our family, then this probability of collision is high if x and y are close in our shift distance. And this probability is low if x and y are not close in our metric. So how do we construct such a family of hash functions if we have an LPHS? So recall that LPHS gives us a distinguished location inside our string. And if two strings are close in the shift metric, then by the definition of LPHS, it is likely that they share the same distinguished location. So if instead of outputting the location and we output the feature that lies inside the location of this distinguished place, then we get such a family of hash functions. And using a general idea due to Andoni and Indik, this gives us the data structure we described. Now for our second application. Recall that Alice and Bob are in New York, and suppose that Alice wants to encrypt some message so that only her physically close friends will be able to decrypt. So she encrypts her message using information that is around her. We want that Jasmine, which is a friend which is physically close to Alice, will be able to decrypt this message using an information that surrounds her, while Bob, which is a friend but which is not close to Alice, will not be able to decrypt this message. How can we use LPHS in order to construct such a location-sensitive encryption? So recall that LPHS allows us to find a distinguished object. This distinguished object is shared between two views that share a substantial amount of information. So because Alice and Jasmine are close to each other, there is a good chance that they will see the same distinguished objects, while Alice and Bob, which are far away, will not have clearly will not have the same distinguished object. Our third application is to homomorphic secret sharing. This concept was introduced by Boyle, Gilboa, and Ishai, and it is the analog of homomorphic encryption on secret shares. Very briefly, HSS allows the user to distribute its input to several servers in a way that allows the servers to compute functions over the input of the user. And meanwhile, the user can be sure that his input is secure as long as at least one of the servers is honest. So among other things, HSS allows to outsource a heavy computational task to compute on remote servers, and it also allows private information retrieval. One nice feature of HSS is that it gives state-of-the-art communication efficiency for several problems. The HSS scheme BGI build uses one-dimensional LPHS. And in the paper, we show that if we have a good k-dimensional LPHS, then the communication complexity of several HSS schemes will be improved by a factor of k. However, it trade-offs with the computation complexity of the problem, but anyways, it improves over the state-of-the-art solution in terms of communication. Okay, so after presenting several applications of LPHS, let us show how to construct good such hashings. We start with a basic construction, which is essentially the Statue of Liberty solution we've seen at the start of this talk. So we define our function h to be the location of the longest streak of zeros inside the first bits of our input string. In the example below, the longest streak of zeros inside Alice's input starts at index 4, hence we define h of x to be 4. Similarly, h of Bob's input is 3 because there starts the longest streak of zeros. Now we see that the shifting property that h of Alice's input equals 1 larger than h of Bob's input holds in this case. And this happens because Alice and Bob share the same longest streak of zeros. What is the probability that this property is going to hold? So they read the same streak of zeros exactly when the streak of zeros does not lie on one of the ends of the inputs they read. So because the location of the longest streak of zeros is approximately uniformly distributed, we have that the error probability is about 1 over d. So this was one construction of LPHS. Let us show another way to build an LPHS, which is based on Kruskal count card trick. This is a nice magic trick. In this trick, you choose any card you want on the top row of the deck of cards, and then you, if you are at card say 4, then you advance 4 cards forward, and if you then at card 2, you advance 2 cards forward, and so on, until you are stuck and you cannot advance more because you will go beyond the end of the deck. Because we want our steps to not be too large, we take our steps to be modulus 10, so Jack is 1, Queen is 2, and King is 3. So where do you finish if you follow this magic trick? So you may want to pause now the video. So you should finish at the card 10. The reason for this is that with high probability, the roots of all cards at the top row will eventually collide, and hence they will get to the same card eventually. So this is kind of what we do in LPHS. We want to get a distinguished feature. The advantage of this method is that we do not read the entire set of cards we have. We only read a small portion of them. And this is how we apply this idea to construct LPHS. By combining the idea of using argmin and Kruskal count algorithm, which is also a Pollard-Skengur algorithm, we are able to construct a much better LPHS. We show that there exists a d delta LPHS with delta smaller than 1 over d squared. This is much better than the argmin algorithm, which has delta, which is of the order of 1 over d. Moreover, we show that for every d delta LPHS, we have that delta is at least 1 over d squared. That is, the algorithm that we constructed is optimal. The proof of the optimality result is easy and relies on the birthday paradox. For the applications, we wanted to generalize our optimal one-dimensional LPHS algorithm to a two-dimensional one. Naturally, we wished that we can just use the same algorithm, but in 2 dimensions. So luckily, argmin algorithm works just fine. However, Pollard-Skengur algorithm does not have a good analog in 2 dimensions. So this construction could not be achieved. And another idea is just to leverage the optimal one-dimensional LPHS and somehow compose it to a 2-dimensional algorithm. Indeed, we can recursively apply a one-dimensional LPHS on columns, where each column, the bit that is present in this point is an LPHS on rows. So the distinguished object is a distinguished column, where in each column we find a distinguished object inside that column. Indeed, this gives a pretty good 2-dimensional algorithm, but it does not give an optimal solution. In this respect, 1 plus 1 is smaller than 2. In our work, we show that we can construct a better 2-dimensional LPHS that is delta equals to 1 over d to the power of 7 divided by 8. And also we show a 2-dimensional LPHS, which we conjecture to get the optimal trade-off of delta equals to 1 over d. And also we prove that one cannot improve the algorithm better than 1 over d. Now I wanted to present how our allegedly optimal algorithm looks like. The algorithm starts with a stage of argmin. That is, Alice and Bob start by reading a square root of d times the square root of d matrix of bits and find the largest block of zeros inside it. If they find the same block of zeros, then they find their shared object and the algorithm is successful. But if not, they proceed to the next stage in which they make a random walk, which is similar to the Kruskal card trick, but this time they also make negative steps. They may go right or left, up or down. As they continue their stages, they increase their step sizes, and the algorithm is quite similar to the optimal one-dimensional LPHS. However, there is a big difference between these two algorithms because in this two-dimensional algorithm, we may run into cycles because we make also negative steps. We overcome this issue by making a deterministic method to exit the cycles. Now, while we believe that these methods enable to get an optimal two-dimensional LPHS, we do not know how to rigorously analyze this algorithm. So we have two relevant open problems. The first is to prove that our two-dimensional LPHS indeed achieves the optimal delta of the order of 1 over d. And the problem is, of course, to analyze the algorithm because of the cycles. And the second problem is to invent an algorithm which works in higher dimension. Say, in 5 dimension, we do not have any idea of how to build an LPHS because, roughly speaking, two random walks in 5 dimensions may not collide at all.